we are now going to go ahead over the last section that we are going to study in this chapter, section 2.8. Section 2.8 will introduce us to the idea of the intermediate value theorem, as a shortcut, IVT. This theorem will describe a particular behavior of a particular class of functions. And it's a fascinating behavior and is extremely intuitive. So if you look at this diagram right here, I have a plane sitting at the origin. I'm thinking of origin, the sea level, or where the airport is located, right there. And the plane is going to climb, and the goal is to climb all the way to 30,000 feet before it levels off. So we want to go from the origin, from the airport, sea level, all the way up to 30,000 feet. And I noticed that I have over here a layer of clouds. And you know that planes cannot be jumping up and down or anything like that. The plane, because this is a real life situation, the plane will have to somehow, it will have to pass through the layer of clouds. It will not be able to somehow magically skip the level of clouds, right? So we know that something like this is going to happen. There, the plane is passing through the layers, and then it's going to go all the way to 30,000 feet. We know that. Imagine then that we have a function f of t, that is giving us the altitude of the plane in the interval from 0 to 20 minutes. And 0 to 20 minutes, if you notice, is marked over here on the time axis. So from 0 to 20 minutes, this function right here, I don't know the expression, it is not important right now, but this function is giving us the height of the plane at every particular time. Because this plane is supposed to behave like planes on Earth, it's a real situation, we know that the plane will have to eventually pass the layer of clouds. This layer of clouds is positioned at 8,000 feet. It will have to pass that layer because the ultimate goal right now of the plane is to reach 30,000 feet. So we know that it's going to have to cross through 8,000 feet. And on top of that, we know that the plane is going to cross the layer at a time right here, a time that is between the 20-minute interval. We know that this time over here is going to be bigger than 0 minutes and less than 20 minutes. It's going to be in between 0 to 20 minutes. So this is everything that we know. If on top of everything, you imagine that this path right here is the graph of this mysterious function, I am going to trace it here in blue. So imagine we're taking a very simple function. So this becomes the shape of the graph. Then what is happening here is that this is saying that there exists a particular time, let me call this time t sub 0. There exists a particular time such that f of t sub 0 is equal to 8,000 feet. But what is really wonderful about this time is that this particular time, t sub 0, has to be between 0 and 20 minutes. And look at the brackets here. I wrote now soft brackets, and that's because t sub 0 will not be 0 minutes. T sub 0 will not be 20 minutes. 8,000 feet is going to happen after the plane takes off and before the plane reaches the maximum height. So that's why I am emphasizing that by putting soft brackets around 0 and 20, by saying that t sub 0 is not going to be 0 and 20, not the endpoints of the interval. T sub 0 is going to be somewhere between 0 minutes and 20 minutes. But we know that because this plane follows this beautiful path over here, it will have to pass through the layer of clouds, and it's going to happen somewhere at a particular time between 0 and 20 minutes. So that's a given. In the next discussion, we're now going to go ahead and be a little bit wilder. We are going to pretend that we believe in aliens, in UFOs, in flying saucers, and all that stuff. And we're going to assume that magic or weird things can happen. Let's see how that goes. All right, so this is the weird situation that I was talking to you about just a few seconds ago. This object right here is supposed to be a spaceship or a flying saucer. I'm going to call it a vessel just to be simpler. Something out of this world, something mysterious, if you believe in UFOs, anything like that. Pretend that this is what is happening. Aliens, they're invading the earth, whatever. So here is my mysterious vessel. And because this is now fiction, it's supposed to be something out of this world, then we can expect for this vessel to behave very differently from the airplane. Now that the question is still the same, will the vessel ever cross the layer of clouds? What could happen? Let's see. What could happen? There you see the vessel going up as if it's going to cross, but then it doesn't. It's now on the other side, and it continues in the opposite direction. So this vessel pretty much skipped, jumped over the layers. It actually literally jumped. Imagine that a function g of t within the same time interval was describing the altitude or the motion of this vessel. Then what would happen, I'm going to trace the path in red here. What would happen is that, for example, the vessel went through like this, but then it somehow magically jumped to the other side, and it gave us this path right here. So here we have the one below the layer of clouds and the path above the layer of clouds. Well, mathematically, doesn't this graph look to you like a piecewise function? All of the sudden, what really happens here, what this path is telling us, is that g of t will never equal 8,000 feet. In other words, there is no t sub 0. Like in the previous case, there is no t sub 0 in the interval from 0 to 20, such that this is true. You will not be able to find a time t sub 0 in the interval from 0 to 20 minutes such that g of t is equal to 8,000. And that's because of the mystery of this vessel. That's because its path, as we move through the path from below the layer, somehow the vessel managed to jump over to the other part of the layer, and then it continued the path. In other words, there is a gap here. There's something doesn't exist here from the graph. The path was completely interrupted. I am hoping that by now you can already start thinking of the sort of functions that are going to ever equal to 8,000 feet. For example, if I want a function f of t to equal to 8,000 feet in the interval from 0 to 20 minutes, then that function cannot have a gap. That function, I don't really care how the shape of the graph looks, but somehow it has to be smooth, super smooth, to be able to pass through 8,000 feet. And whenever that graph is very, very smooth, it is going to connect with 8,000 at a time between 0 and 20 minutes. However, if the graph doesn't have a smooth path, imagine that this is now the path and then somehow it jumps over and continues here, then indeed it will miss the 8,000 mark that should happen right here. Then that means that this function, let's call it g of t, the red graph, then that means that g of t will not equal to 8,000 feet for any time between 0 and 20. So you are not going to be able to find a time between 0 and 20 such that g of t is equal to 8,000. That time is not going to exist. That vessel, that plane will never hit the mark of 8,000 feet. And that's because of that gap right here. That means that continuity of the function is crucial if we want to be able to hit the 8,000 feet mark. The function must be continuous. So continuity, it's a big deal for the intermediate value theorem. Let us now look at the intermediate value theorem, the IVT, in a more mathematical way. No more planes, no more vessels. So we are starting with a continuous function, f of x, right here, continuous, no holes, no jumps, no infinite discontinuities, continuous. We are going to be working on the interval a, b, right here on the x-axis. Well, here is f of a, here is f of b. I'm going to mark them on the y-axis. This is what the theorem says. The theorem says if we choose a value, a real number n, but n is between f of a and f of b. So we are choosing a value, a y value between f of a and f of b. If you have continuity, the function is continuous in ab, and we pick a y value between f of a and f of b, then there exists at least one x value. Here we're calling this x value c. There exists a c, at least one c, such that f of c is equal to n. But the beautiful thing is that c is going to be between a and b. That we know for sure. So again, if we pick a y value between f of a and f of b, this y value, we're calling it n. Then n is going to come from a c, and this c is going to be between a and b. Now, I don't have to have only one c such that f of c is equal to n. I may have more x values whose y values will be equal to n. But the theorem guarantees the existence of at least one. We know that for sure we can count on one such c. Even though we may have more, we can count on one. Here is a case where we have more c's. Again, the function must be continuous. Look at this. Boom. Continuous in the closed interval AB. So here is my interval AB, and I have continuity. Here is f of A, here is f of B, and here is the y value n that we are picking. And this n is between f of B and f of A. Then because of continuity and everything, look at this. The theorem guarantees the existence of at least one c such that f of c is equal to n. But here we have more such c's. Here we have that f of c sub 1 is equal to n. F of c sub 2 is equal to n. And f of c sub 3 is equal to n. How beautiful. So I am going to mark them over here. Look at this horizontal line. This is the first intersection, the second intersection at the same level n, and the third intersection. Again, the theorem doesn't guarantee that we have 2 or 3 or 4 intersections, but it guarantees that there exists at least one. But you must have continuity for this existence to be somehow guaranteed. We have to have continuity. If the graph is not continuous, the intermediate value theorem can guarantee nothing, absolutely nothing. So now let's go ahead and state such an important theorem properly. So the theorem will begin like this. Suppose that f of x is a function that satisfies the following conditions. Number 1, f of x is continuous in the closed interval AB. And notice how this is the first condition that I'm stating, because this is the most important condition. F of x must be continuous in the closed interval AB. If f of x is not continuous, the intermediate value theorem pretty much is useless. Number 2, f of a shouldn't be equal to f of b. And that's because we're going to choose a number n, remember, and n has to be between f of a or f of b. We don't want it to be the same. So this is why. 3, n is between f of a and f of b. So if we have all of these conditions, again, suppose that f is a function that satisfies the following. F of x is continuous in AB, f of a is not equal to f of b, and n is between f of a and f of b. If this is the case, then, and this is the conclusion, then there exists a number C in the open interval AB such that f of c is equal to n. And I want to emphasize here, actually this looks like a hard bracket, supposed to be soft bracket. What I want to emphasize is that the theorem guarantees the existence of a C, not of multiple C's. We could have multiple C's, but we have one for sure. At least we have one. So C has to be in the open interval AB. So C cannot be A, C cannot be B, not the endpoints. It's somewhere in the middle. And what happens is that f of c is going to be equal to that n. Again, let me take you back to the first graph. Here is C right here. C is between A and B, and you notice that f of c is equal, boom, to n. N was between f of A and f of B. So whenever we apply the intermediate value theorem in a problem, we have to make sure that the function in question satisfies these three conditions. If one of those conditions fail, we cannot use the theorem. That's it. We have to have those three conditions to be able to enjoy the conclusion of the mean value theorem. And again, this part over here is the conclusion. This is what the theorem is telling us will happen. If we have continuity, f of a is not equal to f of b, and n is between f of a and f of b, then for sure we know that there exists a c in the open interval AB such that f of c is equal to n. Emphasizing here, notice how I am starting with a piecewise function. Is there a number c in the domain of f such that f of c is equal to 1? What is essential in this problem? And I know that you can probably imagine it. This is similar to the path of the flying saucer, the vessel, in my second illustration. This is how the graph of this function looks right here. Let's put it here in the middle. That's how it looks. So on the left of -2, this is the graph, the line y equals x plus 2. And on the right of -2, this is the line y equals 1/2 x plus 3. In fact, I made a boo-boo here. This is supposed to be a closed dot because we are including -2 there. Okay, so you really notice how there is a gap right here. Look at this gap. And the gap happens between 0 and 2. And it so happens that our n is 1, right? This is n, right here, n. But unfortunately, what's going to happen is that this n right here, 1, falls on the gap. Imagine that I draw a horizontal line over here. See? Boom, it just goes through that gap. So then that means that we can apply the intermediate value theorem. In fact, in this case, no, there is no number c such that f of c is equal to 1. In other words, f of c will not equal to 1. C doesn't exist. And it doesn't exist. C will not exist exactly because 1 lies in the gap of the function. The function is discontinuous at -2. There is a jump discontinuity. So the intermediate value theorem can guarantee absolutely nothing about c. And we know, however, that c is not going to exist. F of x can never equal to 1. Before we start applying the IVT to actual examples, I want us to briefly talk about a particular use of the IVT, and it's a very nice way to use the IVT. Here I have it on top. I'm saying that a typical use of the IVT is to show that a given continuous function has a 0. Or in other words, the graph has an x-intercept in a given closed interval. But I really want to emphasize again, continuous function in a closed interval AB. So we're talking about an f of x and again, our typical closed interval AB. And what we want, what the question may ask you is whether there exists a c. Do we have a c in AB such that f of c is equal to 0? Does that c exist in the open interval AB, right? So we're trying to see whether this particular function has a solution, or if you're thinking about it graphically, whether the function has an x-intercept. Here is the graph of a hypothetical f of x, and look at f of x is beautifully continuous right here. So we have continuity and we have a closed interval AB. And look at this right here. Here is f of a. Here is f of b. F of a is negative. F of b is positive. So because f of a is negative and f of b is positive, 0 is in the middle. In other words, I know that f of a is less than 0, less than f of b. So, because I know that 0 is between f of a and f of b, and the function is continuous and everything else, then the IVT will say that indeed there exists a c in the interval AB such that f of c is equal to 0. The IVT guarantees it guarantees that the function, look at this, imagine that we are at f of a, the function will cross through the x-axis. So this is where you have c. C is going to be right here. The theorem guarantees that the function is going to climb. It will have to pass through the x-axis. It will have to cross through c in order to continue all the way to f of b. In other words, it cannot be such that the function is going to somehow skip the x-axis and continue on the path. And it will not do that because we have continuity. So, continuous function, f of a is negative, f of b is positive. Because f of a and f of b have different signs, we know that the function is going to have to cross through the x-axis. So c is going to exist. I mean, the graph may cross several times in the interval AB, but we know that for sure we have one x-intercept. Now, the IVT will never give you the value, the actual value of the x-intercept. It will never tell you c is 1.3. It will never give you the value. It will just tell you that it exists. C is there. We don't know the value, but we know that it's between A and B. All right, so let's see, how do we put the IVT into practice? This question is asking us to show that the following polynomial has a 0 in the interval 1, 2. Having a 0 really means that graphically it has an x-intercept between 1 and 2. It may have more than one intercepts between 1 and 2, but we want to show that it has at least one. So graphically, just imagine. I don't know how the graph looks, and honestly, I don't need to know how the graph looks. But what we want to show is that in this interval right here, the function is going to cross through the x-axis. We want to be able to show that this c value exists. And the IVT, I think, is going to be perfect here because look at the function. It's a polynomial, a third-degree polynomial. Every polynomial is continuous in its entire domain. The domain of a polynomial is all real numbers. So f is continuous in the closed interval 1, 2. I'm going to go ahead and say that immediately. Number 1, we know that f is continuous in the closed interval 1, 2. Now, I need to show somehow what I want to show. Let me write it here. I want to show that f of x is equal to 0 in the closed interval 1, 2, right? That's what I want to show, that is equal to 0. So what I would like to do here is to figure out what is going to be f of 1, because notice 1 is A, 2 is B. So naturally, I would love to know what is f of 1 and what is f of 2, right? That the intermediate value theorem requires information about f of A, f of B. So in this case, f of 1, f of 2. So let's calculate f of 1. F of 1 is going to be equal to 4 minus 6 plus 3 minus 2. That is going to give us negative 1. And look at that, negative 1 is less than 0. Now let's do f of 2. F of 2 is going to be 4 times 8 minus 6 times 4, right? 2 squared is 4, plus 6 minus 2. So practically, I am substituting 2 into the polynomial. That is going to give me 32 minus 24 plus 4, which is going to give me 12. And 12 is bigger than 0. So what do I conclude from these two pieces of information here? I conclude that f of 1 is going to be less than 0, and 0 is less than f of 2. That means that 0 is between f of 1 and f of 2. Remember that 0 is your n. N is 0, and 0 is between f of 1 and f of 2. So now then, this is where you can now use the conclusion of the mean value theorem. Because 0 is between f of 1 and f of 2, so we're going to say here that since indeed 0 is between f of 2 and f of 1, then there exists a c between 1 and 2 such that f of c is equal to 0. So what that means is that indeed f has a 0. It has a 0 in the open interval 1, 2. Okay, it has an interval. Now, we don't know what the value of c is. Again, we don't know if c is 1.5 or whether c is 1.8 or whether c is 1.03. We don't know. We just know that c exists and is going to be between 1 and 2. So this c right here that I'm circling here, this c exists and is going to be between 1 and 2. And that happens by the intermediate value theorem. Example 2 is asking us to show that g of x, which is equal to x over x plus 1, a rational function, takes on the value 0.599 for some x between 1 and 2. Takes on the value. That means that we need to show that we can find an x such that g of x is equal to 0.599. But again, this x has to be, and I'm going to put soft brackets because that's what the IVT will guarantee. So x has to be between 1 and 2. So how can I use the IVT in this situation? Well, in order to use the IVT, I have to make sure, number one, and please make this always your number one check. You want to check that your function is continuous in the interval 1, 2. And you notice that this function is continuous in that interval. The only place where this function is discontinuous is at -1. So I'm going to put over here that x cannot be equal to -1. At any other value of x, g of x will exist only at -1. But nicely, -1 is not in this interval. So we will say here, number one, to note that g of x is continuous in the closed interval 1, 2 because its domain, the domain of this function, happens to be between from -infinity to -1, not including -1, union not including -1 to positive infinity. So pretty much what we are saying here is that -1 is the only problem. Any other value of x will be fine with the function. So we have continuity in the closed interval 1, 2. And please note that it is okay to be a bit elaborate when talking about continuity. Continuity is a must. If the function is not continuous in the interval in question, the IVT cannot be applied. So might as well check for continuity carefully. Now let's go ahead and continue with the second condition. We now have to check g at the endpoints. So what is g of 1 and what is g of 2? So g of 1 will be 1 over 1 plus 1. That's going to give us 1/2. Let's say 0.5. And then we're going to check g evaluated at 2. So 2 over 2 plus 1, that will be 2 over 3, approximately 0.67. Let's actually say here 0.5 to have 2 digits. Look at this fabulous result. What we now have is that 0.599 is less than 0.67, but is greater than 0.50. In other words, what this is telling us is that since g of 1 is less than 0.599 and 0.599 is less than g of 2, then we know for sure that there exists an x in the open interval 1, 2 such that g of x is equal to 0.599. And this fabulous conclusion happens by the intermediate value theorem. By the intermediate value theorem, we can now guarantee the existence of this x. This x exists such that g of x is equal to 0.599. And we know that x is going to be in the interval in question, the interval between 1 and 2. Example 3 will expose us to another useful technique when working with the IVT. Example 3 says to show that cosine theta equals theta has a solution in the interval 0, 1. Now, notice how they gave us an equation. They didn't give us a function. The IVT requires a function, requires a continuous function. To apply the theorem, to use the intermediate value theorem, we have to be using it with a function. And here they didn't give us a function. But nobody's stopping you from creating a function that is going to be related to this equation, so that when you apply the IVT will guarantee the existence of a solution to this equation. So this is what I have in mind as a function. I am not going to somehow magically come up with a function. I am going to look at the equation that I have right here, and I am going to bring the right side, theta, to the left side, and that will make my function. For example, I will say let f of theta equals to cosine of theta minus theta. Look at that. And then what I am going to try to show is that this function has an has a theta intercept in the interval 0 to 1. How beautiful, because how is that helpful? Let's do it here on the side. Imagine that I can conclude that f of theta is equal to 0. What does that imply? That implies that cosine of theta minus theta is equal to 0, which means that cosine of theta is equal to theta. And here is the equation that you were asked to show that has a solution. So if I can show that f of theta has a theta intercept, like an x-intercept, in the interval 0, 1, then this is going to follow, and therefore this will follow, and therefore that will follow, and you're going to be done. So let's go ahead now and work with f of theta. And now that we have a function, we can apply the IVT to that function. So condition number 1, as always, continuity. we're going to say here that f of theta is continuous, in the closed interval 0, 1, since cosine of theta and theta are continuous. They are both continuous in 0, 1. And remember that back to section 2.4, if we add and subtract continuous functions, we get another continuous function. And here I have the difference of cosine theta and theta. Theta is like saying cosine x and x. They're both continuous. So cosine theta and theta are continuous. So then that means that the difference is continuous as well. So continuity is there. Now I am going to consider f of 0, and I will consider f of 1. So f of 0 is going to be equal to cosine of 0 minus 0, and we are assuming radians here, never degrees, always radians in calculus. Cosine of 0 is going to be equal to 1 minus 0, that means 1. 1 is positive, bigger than 0. Now let's consider f of 1. F of 1 will be cosine of 1 minus 1, and with your calculator in radians, you will approximate this as negative 0.4597. The point is that this is negative. So here again, I now have that negative 0.4597 is less than 0, and 0 is less than 1. So what is that telling us? This is telling us over here that f of 1 is less than 0, and 0 is less than f of 0. In other words, 0, which is like n from the previous discussion, n is between f of 1 and f of 0. 0 is between f of 1 and f of 0. So the intermediate value theorem will say the following. Since f of 1 is less than 0 and 0 is less than f of 0, then for sure there exists a, what do we call it? A theta. There exists a theta in the open interval 0, 1 such that the following is true, such that f of theta is equal to 0, the number in the middle, this n right here. Well, but then that means that since f of theta is cosine theta minus theta, I can take f of theta and I can replace that with cosine theta minus theta. And that means if I solve this, if I isolate cosine theta is equal to theta. And this is exactly the equation that we were trying to show that has a solution in the interval 0 to 1.